Now coming to a screen near you, please welcome Yotam Mazurik, Senior Security Researcher at Pentera, as he discusses the blind spots that come with IPv6.
Hi everyone, I'm Yotam, a security researcher at Pentera. I'm really glad to be here today, and I hope everybody is enjoying the exposure event. Today we'll be talking about IPv6. Before we jump to the interesting part, a few words about myself. I'm 24 years old. I live in Israel, near Tel Aviv. Love surfing, snowboarding, climbing, and all sorts of extreme sports. I'm an ex-Navy officer, and I've been working now for about half a year in Pentera's research group, specializing in network security. As part of my latest research that is currently being implemented on top of the Pentera platform, I'm very excited to share with you the unseen attack surface, IPv6. We'll talk a little bit about the accelerated growth in technology, then dive into the Internet Protocol. Afterwards, I'll walk you through an attack vector abusing IPv6, and finally, we'll cover some mitigation options. We live in an era where technology is advancing in such a rapid pace. A few decades ago, the internet didn't even exist, which is something unimaginable by itself. Not to mention social media, which takes such a big part of our lives. And even though cars were invented almost 2 centuries ago, since the first smartphone was released, it took only a few years to invent the navigation apps and change the whole aspect of driving. iOS apps were originally in-house developed by Apple. Since Apple has opened the App Store to third-party developers, each year, hundreds of thousands of apps were developed. Imagine starting with just a few hundreds and ending with being responsible to a couple million pieces of code, not even written by your own employees. This is just one example of many to how such an accelerated growth can change the game in aspects of security. Before we jump to the attack vector, I want to give a brief explanation on the Internet Protocol. Most communication between computers is done over the Internet Protocol. In order to communicate, each endpoint has its own unique IP address, which other computers can use to send it data. Think of this as if you have ordered a package on Amazon. The package will of course arrive to the address you've stated. The same happens in computer communication. A computer may send data to other computers based on their IP address. This protocol is one of the basic building blocks to computer network communication. It enables us to SSH a remote machine, access our Facebook account, and even send emails to friends all over the world. The first version of this protocol, which I guess you're all familiar with, is IPv4. The first IPv4 network was deployed back in the 1980s and was designed to support a few billion addresses. Although it might seem a lot, the internet has grown exponentially. Nowadays, almost every person has at least one personal computer. Some have IoT devices in their homes, and even cars are connected to the internet. Eventually, it was obvious that the existing architecture isn't suited up for the future. The common term for this understanding is the address exhaustion of IPv4. Like in any shortage situation, new solutions were invented. The first is NOT, which I will not cover today, and the other one is IPv6. I guess you've all heard this scary term before. Actually, IPv6 is just a newer version of IPv4. I cannot say that they are the same, but for this presentation's purposes, they serve the same goal, which is to allow computers to communicate. Just so you'll be familiar, this is how an IPv6 address looks like. Pretty scary, huh? So what did IPv6 come to solve? The main problem IPv6 tries to overcome is address exhaustion. In IPv6, there is an enormous address space compared to IPv4. It also comes with enhanced security as it implements IPsec inside the protocol itself, independent of other network layers. Another win on the operation side is that networks can be stateless configured, which should ease management. With all these benefits, I would expect everybody to adopt IPv6 by now. So why haven't it happened yet? It is clear that transitioning from IPv4 to IPv6 is not an easy challenge. Most services are based on IPv4, and as we all know, transformation takes time and money. While transition may be difficult, there are different ways to adopt IPv6 while maintaining compatibility with IPv4. Some strategies, like dual stack, tunneling, and header translation, may provide a solution. ISPs all over the world have started transitioning to IPv6. It seems like some sectors have already taken the lead, like mobile operators in North America. As a matter of fact, they are so ahead in the process that they have even started turning off IPv4. Since it was launched in 2012, the adoption of IPv6 in the public area has grown significantly. According to Google statistics, France has the highest usage rate at almost 75%, while the US is just under 50%. While IPv4 is still the most common used internet protocol around the world, since the mid-90s, IPv6 has silently entered our lives. The earliest implementation was in the Linux kernel. Not much after, it was implemented in network gear such as Cisco iOS, and eventually in both Windows and Apple operating systems. This means that what we are going to discuss today most likely impacts all of you. Remember the weird-looking address from before? On Windows, IPv6 is enabled defaultly. On macOS computers, it is set to be configured automatically, which is pretty much the same. And of course, in Linux distributions, such as Ubuntu, we can see an inet6 address enabled default. I'd like to take a quick pause and summarize what we've talked about so far. So we have this not so new technology, which is called IPv6. It is a newer version of the old IPv4 and is defaultly enabled on all common operating systems. I guess we all know what this means. Yep, a new attack surface. New CVs addressing flaws in IPv6 are found on a yearly basis. Some, as in CV 2022-34718, allow attackers to achieve remote code execution on Windows operating systems based on flaws found in the kernel. Others, like CV 2021-27862, allow attackers to bypass security mitigation in network gear, such as RAGuard. When I prepared the presentation and searched MITRE for IPv6, I found no results, which was really concerning. While I was rehearsing for today's session, I found that there are still no tactics and techniques regarding IPv6 in the framework, but we see threat actors starting to leverage IPv6 in their campaigns. By leaving out tactics and techniques regarding IPv6, organizations which rely on these kinds of framework will consider themselves secured, while attackers may take advantage of these blind spots. Now I'd like to walk you through an example of a known attack leveraging the design of IPv6. In this example, we have a small IPv4 managed network of two endpoints. Both endpoints are connected to the switch so they can communicate without passing through the router. The router acts as the network's gateway towards the public internet. Because our attacker is about to abuse a flaw in IPv6, his interface is of course enabled to IPv6. Our network is IPv4 managed, so IPv6 routing is not enabled on the router. The blind spot our attacker is about to take advantage of is that the victim is IPv6 enabled and accessible, but have yet been used. Usually, when I want to access a resource on the internet, let's say Gmail, I will send a request through my gateway towards the destination, in this case, Google servers. And of course, I will need to send my credentials in order to authenticate. Some design elements in IPv6 that may affect unsecured networks allow attackers to push new IPv6 configuration to a remote computer. To be more specific, this attack is server-initiated and not client-initiated. Let's take a look at two examples of network configuration. The first one is configuration sent by ICMPv6 router advertisement. As we can see, the attacker can set not only the IPv6 address derived by the prefix information, but also a list of additional DNS servers. The same applies to configuration sent over DHCPv6. Again, a new IPv6 address and a list of additional DNS servers. These screenshots were taken from a Windows victim that has been exposed to such attack. We can see on the bottom, a new DNS server has been applied. And on the top, two new IPv6 addresses are configured, the primary address and the temporary address, which is usually used. By influencing the victim's IPv6 network configuration and creating sort of a man-in-the-middle situation, an attacker may hijack the victim's DNS traffic. To keep it simple, hijacking DNS traffic may lead to redirecting the victim towards other malicious servers. For this example, I chose to stick with Gmail, or in our case, a malicious Gmail. Our victim wants to read some emails. So before he accesses Gmail, our attacker redirects the request towards the fake Gmail server. The fake server will have a valid certificate and will look just the same as Gmail, so the victim will not suspect anything and insert his Gmail credentials. I chose to give an example on websites, but this attack can be used to redirect other protocols such as SMB and SSH. Now let's see what action we can take to mitigate from this attack. There is no single solution to address this problem, so I chose a few suggestions. The first one is to disable IPv6. This can be done by GPO, as in this picture, or by any other means. Router advertisement guard allows transmission of network configuration sent over ICMPv6 only from known trusted interfaces, such as a router interface. In case an untrusted interface, such as interfaces connected to regular endpoints, will try to transmit network configuration, the packet will be dropped. DHCPv6 snooping is pretty much the same. It allows transmission of DHCP offers only from trusted interfaces. Last but not least, the good old peer port segmentation, which provides an additional layer of security as we isolate each endpoint in the local network. Before we finish, I want to sum everything up. Technology is changing on a daily basis, making it pretty difficult to adapt. IPv6 will keep increasing its footprint in terms of computer communication. And while it seems like the IT operations side is adapting to the change, I think so should the security community. With that being said, try to stay aware as possible and keep optimizing for your exposures. Thank you very much for your time today. If you have any questions, feel free to reach me via email. Check out other research from Pentera Labs on our website.
Thank you, Yotam. This is certainly helpful information for every security professional.